Okay, so woohoo. Woohoo! All right. Okay, so director graphs. Okay, so even with cycles, we got cycles. Yeah, there's a theme to these doodles. Okay, lecture in a minute. So far, this first half, you should know. What is the idea of DFS? How I learned to love the stack. Okay, that's the idea of DFS, right? That's a powerful sort of paradigm to understanding DFS and what it can do for you. Okay? So there's post under numbers. Those are telling you time on stack. We're going to review this real quick anyway. Topological ordering, which is that the inverse post-order number is a topological ordering of the graph. Okay? And another way, I gave you two algorithms for that, is remove a source and repeat. Okay, so what we're going to do next is we're going to define this notion of strongly connected component, the strong connectivity in graphs, and what it means is that U and V are connected if there's a path from U to V and V to U, or they're on a cycle together. Okay? That's the idea of strongly connected component. Now, once you do that, you could easily sort of tell which guys are in the same component in order V times E, just using breadth first search from each vertex and back, and check whether who's reachable from who, and if they could both reach each other, then you're done. Now I'm going to show you a linear time algorithm for strongly connected component. And the observation is going to be doing something along the lines of what we're doing. The reason I'm really making sure that I do a quick review, the actual algorithm here is going to, in some sense, do both of these algorithms for topological ordering. It's going to use a post-order number for DFS, and it's going to do this remove a source and repeat sort of algorithm for topological sorting. Both of those elements are there. Okay. And so at the end of the lecture, you should know all this. At the end of the lecture, after you do the discussion, after you do the homeworks, and after you've read the notes, you should know all this. Okay? So this is just the first iteration, or whichever number of iteration you're on. Okay. So all teachers know the learning happens when you're doing. This is just framing. Okay? This one pass. Okay? How I learned to stop worrying and love the stack. That's what the DFS is about. It's a joke. But none of you know it because you don't know this movie, Dr. Strangelove. Who knows it? Yes! Okay. Sorry. I shouldn't have yelled into the microphone. That was rude. Yes! Okay, sorry. Okay, so it's a movie. The phrase in the movie is, how I learned to stop worrying and love the bomb. And it's sort of a dark movie sort of about nuclear blah, blah, blah. That was the fear of the time. I guess these days it's climate change. Back then, people were all worried about getting blown up by nuclear weapons. Times change, I guess. So anyway, so there's this notion of pre and post intervals for a graph for DFS. Okay? So pre is the first time you put the node on the stack, and post is the time when you pop the node off the stack. And when I say put the node on the stack, what I mean, put the explore call on the recursion stack. Okay? But you don't have to use a recursion stack. You could actually just implement the algorithm with the stack and not ever use recursion. But here we're sort of using recursion, okay, to say we're putting nodes on the stack when we start exploring them. We pop them off the stack when we get out of that procedure, just as you did in 61A. Okay? If the stack ever looks like this, who is an ancestor of whom? V is the ancestor of U, right? You explored V first, and then the explore calls keep piling up, and at some point you explore U. And the reason they're on the stack at the same time is there's a sequence of explore calls from V to U. Each sequence corresponds to an arc, or an edge, right? Each step in that sequence corresponds to an arc. So V is an ancestor of U, okay? Okay, so no cycles means there's no back edges, Okay, and a graph. Okay, so we talked about that. A back edge is an edge to an ancestor in this tree of explorer calls. Okay? Now, topological order. So now if there's no cycles, there's no back edges. That's what you know about directed graphs. Okay? Or even undirected graphs, that's true. Okay, so topological ordering, a directed graph, means every arc. Now, in a directed graph, edge UV means an arc directed from U to V. U is the tail, V is the head. Okay? And now what you're doing is you're ordering it so that in that order, U is before V in that ordering. Right? Hello is before goodbye in the example I used before. Okay. Now, we argued that the inverse post-ordering is a topological order. And we also argued another, and I'll go over that real quick as well, because it's going to really be central to the strongly connected components algorithm. Okay, and then we also talked about another algorithm for topologically ordering, and that's remove a source and repeat. Okay, so these are all things that you should get continually more comfortable with. Okay, so for search directed, you can watch the sequence of explorer calls. I don't know. Just to remember, I use the same example every time, or most times, because I'm trying to build up intuition about different algorithms rather than also throw new examples at you. Okay, so this is the thing. What are the black numbers? Pre. What are the blue numbers? Post. Right. Okay. So what's the last vertex that's popped off the stack? What's the first vertex that's popped off the stack? C. Yeah, this is harder, right? It doesn't really tell you much, the first vertex that's popped off the stack. But the last one seems to have some information in it. Okay? So, and we have these notions. We have these tree edges, which are colored in red, and this other color, I think it's purple. And the key to them is this interval. Okay, forget this. Think about it yourself. Who is in which? Okay, is U in V's interval or is V in U's interval? If it's forward. If it's tree edge, V's interval is inside of U's interval. And that's what we're saying. Okay? And here's a forward edge. F's interval, it's a descendant. That's what it means. It's an edge to a descendant. And the descendant is the call of Explorer on this descendant starts at A. You explore A, then at some point you explore E, and then at some point you explore F. Okay? So the interval for F, which is 10, 11, is inside the interval for 0 to 13. So the back edge int V, it's just a back edge, it's just the opposite, right? This is a back edge, an edge. A forwarded edge is an edge from an ancestor to a descendant. A back edge is an edge from a descendant to an ancestor. Okay? Pretty simple. Okay, and there they go. And then the cross edge is this thing here is a cross edge. It's sort of saying, okay, why don't I need to explore this? Because I already explored it before. Right? Through a different sequence of explorer calls. Okay, so this is a cross edge. It's not in the tree because you're not going to explore across it because we've already explored D. And it's not an edge to the ancestor, or it's not a forward edge. So it's just the other thing. Okay? And what it means, and why, when we explore D, then we not explore F? We explored D first, so shouldn't we have crossed this edge and explored F? No, obviously not, because it's directed. Well, am I smoking something? No, you want to go this way. It's directed, okay? It's all legal now anyway, so it's fine. Okay. So testing for cycle. Let's just go a little bit more. Now that we saw the example, it's all paged back in, and I'm going pretty quickly. Let's just do a little proof. Okay? A theorem has a cycle if and only if there is a back edge or a sketch of a proof. Okay? The back edge says there's a cycle, because why? You have an edge to an ancestor, and the ancestor, by definition, has a path to you. Right? That's the sequence of explorer calls that came to you. Okay? So that forms a cycle. Okay? Now, the other way, once you have a cycle, you need to show there's a back edge. So let's think about a cycle. Let's think about the first vertex on that cycle, V0. It's the first vertex explored on that cycle, right? So you're going to explore every other vertex on that cycle before returning from V0, because you have a path to them from V0. Okay? Okay, so therefore the interval for V0, the pre-post interval, contains the intervals for all the others on that cycle. Okay? So now the edge from the last vertex, its interval is contained in the interval for V0. Okay? And now that edge is a back edge, because if an edge goes from somebody whose interval is contained in somebody else's interval, it's a back edge. It's an edge to an ancestor. Okay? So that says there is a back edge if there's a cycle. So it's an if and only if. There's a back edge if there's a back edge implies the existence of a cycle, and a cycle implies the existence of a back edge. Okay? So now topological ordering is this ordering pi, where for all edges, in the ordering, U is before V. Okay, pi is just the ordering. So the reverse order, if you output nodes in reverse order of post number, it is a topological ordering. Okay, and why is this true? First of all, if there's no cycle, can there be a back edge? No back edge. It's true because there's no back edge. Okay? And this is why. That's the proof. No back edges. So then there can only be these tree edges or forward edges. Okay? So now the tree edge, the tree or forward, it should be that it should be that this interval contains this interval. Okay, I've switched the things. Wait, forward edge. Yeah, this interval is contained by this interval. That's correct. Okay? I mean, my notation, I should probably switch the symbol. But that's what that symbol was meaning to mean. So if this interval is contained in this interval, then that tells you this post-order number is greater than this post-order number. Right? Okay. And the cross edge, you just work it out. It's the same thing. It says that this whole interval is before this whole interval, is after this whole interval. Okay? Now, if this whole interval is after this whole interval, that says this post is greater than this post. So for every edge, you have every edge, UV, you don't have back edges. For the other two kinds of edges, post of U is greater than post of V. So reverse post-order number will give you a topological sort. Okay? Okay. Yeah. He's asking if a graph has a cycle, we cannot do topological sort. Okay, that's a good question. Does everybody see what the answer is that? Why can't we do topological sort on a graph with the cycle? Right. Okay, so topological ordering is where for all edges, the edges only go in one direction. If you have a cycle, won't one edge have to come back at some point? That's the idea. So this condition cannot be met. Does that make sense? Because like a cycle says you go forward, forward, forward. At some point you need to come back to this node. So there must be some edge somewhere that goes backwards. Right? That's what a cycle is. Okay? So if the social norm was that I have to say hello before I say goodbye, and I have to say goodbye before I say hello, society would collapse. Right? That doesn't work. Right? Okay. Yeah. Or the social norm has to change. So. He asks, is there a way to get the topological number orderings with the pre-numbers? And I don't think so. I think if I was given the pre-numbers alone and not given the graph, I could not output a topological order for all graphs. I mean, they may work for some graphs, but it won't work for all graphs. I believe. I can construct such an example. But okay. Okay, so that's that. Okay, that's a quick review of last time. And now this lecture will be really easy because it's some combination of those ideas. Okay, a new definition which you have to parse and understand. And then after that, you just combine those other ideas because you understand them really well, and then you can move on. Okay, so here's Oh yeah, this is an example. This is an example. I'm just repeating it for you. When is A popped off the stack? This is the question I asked before. I'm asking again. When is it popped off the stack? Right. So last plus induction implies that the reverse order of the post order number is topological order. Okay? So that's essentially what we did. All right? Okay. Okay. Again, I'm sorry to beat a dead horse, but what is A or B? Yeah. Good. Okay? Any questions? Okay. So two nodes are connected in directed graphs. What does it mean to be connected? When are they connected? Okay. When there's a path from U to V, does that make sense? Should that be the definition of connectivity? It is in undirected graphs. How about when there's a path from V to U? Which one of these should be the definitions of connected? Right. Okay, both. Good, right? You have to have both. Okay, they're both not the definition of connected, but the definition is that both must happen for them to be connected. And we do really, we're careful because people may want to choose different things, so we call it strongly connected. Two vertices are strongly connected if there's a path from U to V and there's a path from V to U. So nodes are, and we also sort of define, we specify that nodes are strongly connected to themselves. We consider a zero-length path or a one-length path to be a path from a node to itself. Okay? Path with zero edges in both directions. Okay, so this is the properties. This is the sort of basic case that nodes are strongly connected to themselves. Okay, so here's a true-false question. U is strongly. I should have said the implication should have said strongly. U is strongly connected to W. Is this true? Okay. So we have a path from U to V to V and then to W, right? Because we have a path from U to V because U is strongly connected to V. And we also have a path from V to W because V is strongly connected to W. Okay, so there must be a path from U to W. And similarly, we have a path from W to V because it's W and V are strongly connected. And we have a path from V to U because V and U are strongly connected, right? There's paths in both directions. So therefore, there's a path from W to U. So there's a path from U to W and a path from W to U, so therefore W and U are strongly connected. Okay? Intuitively, it's fairly clear. There's the argument, maybe my argument actually makes it less clear. It's almost obvious, right? Okay. Okay? So it's transitive. It has this notion of transitive. This relationship of strongly connected is I am strongly connected to myself. Okay? If I'm strongly connected to Professor Raghavendra and he's strongly connected to Professor Vazirani, I'm strongly connected to Professor Vazirani. So it's transitive. Okay? And so then what you can do is you can partition the nodes into equivalence classes, like you could do for connectivity in undirected graphs. Right? We did this in 70. I'm sure everybody does this in 70. We talk about connected components in the Eulerian algorithm. Okay? So what it is if you take all the things that are strongly connected to each other and you put them in a group. Okay? And you can partition the graph into these groups. They are non-overlapping. Okay? Okay. Strongly connected nodes are the maximal sets of nodes. The maximal sets of nodes which are strongly connected. Okay. So here's an example. Do you guys see the strongly connected components here? That's strongly connected. Okay. So let's just collapse them. Let's do something. Let's take this set of nodes. Each of these clouds are strongly connected components, right? B, C, D is a cycle. So B is connected to D, D is connected to B by a path. C is connected to B. There's a path from B to C. There's a path from C to B, so on. All the red nodes there are in this red strongly connected component B, C, D, right? And The blue nodes, A, E, F, they're all strongly connected to each other. G is sad, all by himself over there, and he's in a strongly connected component by himself. Okay? Now what I did is I grouped them, and then I collapsed, so I got rid of the graph inside, and then I just said, well, if there's any arc from AEF to G, I put in an arc from this blue cloud to this green cloud, right? And if there's any arc from BCD to G, I put an arc from BCD to G. Okay? If I see any arc from AEF to BCD, I put an arc from AEF to BCD. If I see any arc from BCD to AEF, I put in that arc back. But are there any arcs from BCD to AEF? So I don't put an arc there. Okay? Do you notice something about this graph? Yeah, if you collapse them and think of all those clouds as nodes, it's a DAG. It has no cycles. Right? Right? If you think about those and you put the edges in the way I said, it's good. Right? Okay. So this is interesting, right? Okay, any cycle, if you had a cycle here, if I had something from BCD back to AEF, what would that do? That would tell you first of all, there's a path from A to every node in E, every node in the blue thing. So you can go from A to whichever node is the tail of this arc, go over to this strongly connected, and get to B, the graph, and get to B. And similarly, you can get from B to any node in D, and if there's an arc backwards, I should have drawn the arc in red or something, backwards, then you'd have a cycle that involved nodes in these two. And they would be the same strongly connected component. Okay? Any cycle would collapse the nodes in that cycle into a single strongly connected component. Everybody would be reachable from everybody in both directions. Okay? Okay, so now there's a structure of these components. Right? And connected components in undirected graphs, there were no edges between any of the components. That's what it meant to be connected components in undirected graphs. Strongly connected components in directed graphs means that the arcs between them form a DAG. Okay? Okay. So every directed graph is a DAG of strongly connected components. That's the property. Okay. So now the question is, how do you find the strongly connected components? Okay, so let's say remember, let's go back to explore. Okay? If I start and explore at a vertex U, it visits all the nodes or explores all the nodes reachable from U. That's the basic property of the Explorer procedure. Right? Okay. Okay, so here's an algorithm. If I run Explore on the node in the sync component, what will it do? No, it'll explore G. Right? It does almost nothing, but it explores G. Right? Okay, so it explores G. Okay, now there's only one node in the sync, so you can get rid of those nodes. And then you output all the visited nodes and say that's a connected component. So in this graph, if I ran an Explorer in a sync component, I'd get back G, I'd remove it from the graph, and then I'd output G as a connected component. Right? As a strongly connected component. Okay? And then I repeat. After I do G, which one should I explore next? Run Explorer on a node in the new sync component. If I remove G, what's the sync component that's left? The red one or the blue one? Which one's the sync component? Red, because it has no outgoing arcs. The sync component means it has no outgoing arcs. The component G has no outgoing arcs. Okay, so this is very nice, right? Let's say I did something else. Say I ran Explorer on a node in the blue thing. I could discover the whole graph. I didn't find a connected component. But if I explore a strongly connected component, but if I run explore on a node in the sync component, what I get, what I explore, are the nodes in the sync component, right? And then I can output them. I say this is a component, right? Because it's in the sync component, and I got everything in it. Okay? Yeah.
How do you know what your sync component is if you haven't already identified the strongly connected components?
Yeah. Okay. So he said, how do you know what your sync component is if you haven't already identified the strongly connected components, right? And somebody else said yeah, and somebody else said yeah. What they're telling me I'm a jerk. I'm not telling them the whole algorithm, right? And that's true. I haven't told you the whole algorithm. Okay. So yeah, this is fine. This is ridiculous, right? I don't know sync, right? I was reading a lecture note from a colleague in university. It's too long of a story, but at some point, he says when you do the circular reasoning, it's hilarious. So is it hilarious? I don't know. I think it's hilarious, but okay. I should get back to what are we talking about? Oh yeah. Okay. So strongly connecting components, right? So this would work, but it's nonsense. But it's almost right. All we need to do is this. Okay. If I knew how to do this, I don't have to identify all the strongly connected components. I just have to identify one node in the sync component. And then I have to be able to do it again. Okay? So that's what I need to do to finish this algorithm. Okay? And not only that, now let's say I can do that efficiently. Say God gives us an oracle or God, depending on whether you're religious, or Greek. Tells you a node in the sync component. That's all you need. You don't need all the nodes in the sync component, just one, right? If they tell you what's a node in the sync component, this is linear time, right? Because you only explore G, so the total work from the first call to explore only looked at G. It didn't look at any of the other nodes. So every time it outputs something, it outputs only the nodes it touches, and it only touches each node once, right? This algorithm. So this algorithm is wonderful except for this fact that we don't know how to identify a node in the sync component. Okay? Oh, yeah. Okay? So that's what we want to do. Any guesses how we do that? Check the adjacency list. But I spent a lot of time on why we love the stack. Okay? And in particular, the topological ordering, what told us a node in the source? What told us a source? Could we find a source with the post order numbering? Is the last node popped off the stack a source? Right? Because that's the first one. We put it first. There can't be any incoming arcs. So I know. So in some sense, the post order number is telling me something about the graph where it tells me a source. Right? Okay, I want to sync. Okay, sync source. Okay, well, there's some issues. Okay, so, right? That's what we showed last time. That's why we talked about this topological sort and post-order number and how I love the stack. Okay? The highest post-order number in any depth first search is a source because it's the first one output by the topological sort. Okay? Moreover, we can say something like generalize this. It's a little ugly to generalize it, but we can do it to graphs with cycles. Okay, that was something that very strongly depended on no back edge, right? But there's back edges all over this graph. There's cycles all over this graph in general. But they have a certain property. They stay inside of strongly connected components, the cycles. Okay? So what we talk about here is instead of thinking about individual nodes, we start thinking about strongly connected components in the strongly connected component graph, which is a DAG, right? The strongly connected component graph is a DAG. So we can then think about this topologically sorting of that DAG, okay? And now what we're going to say is if C and C prime are strongly connected components with an edge from C to C prime, the highest post-order number of a node in C is larger than any post-order number of a node in C prime. So it's a more complicated property, but this is what it is, okay? So let's look at this property. Just make sure you understand. Okay? So this is the graph. This is this is just a graph, and this is a strongly connected component graph. It's a DAG, okay, that's associated with the strongly connected components. Okay. Now we wrote down the post order numbers, right? Remember, this was the last one, 13. Okay, and what am I saying? I'm saying that now I'm replacing each node here, each vertex here, with their post order number. Okay? So now let's parse the statement with this figure. Okay, what it's saying is that, look, here are two connected components, C and C prime. Strongly connected components, C and C prime. It says the highest post order number here, what is the highest post order number here? 13. Is higher than any post order number there. Is that true? Right. 13 is bigger than 8, and 3, and 4. Right? Okay, now let's look at two other strongly connected components. Let's look at the red one and the green one. Okay? What is the highest post order number in C, right, in the phrase if C and C prime, with where C has an edge to C prime? In C, what is the highest post order number here? 8. Now, is 8 higher than 7? Yes. Yes. Okay. Okay. So that's what it's saying. That's what we're saying. It did not say here the highest post order number in this graph was 8, was B. It says that highest post order number of B is higher than the post order number of 7. It's not saying every node in here has a higher post order number. Right? Just as one does. Okay? So, like 3 doesn't have a higher post order number than C doesn't have a higher post order number than G. Right? It's a little complicated, a little subtle. It's not saying, you got to make sure it's saying exactly what it says and only what it says. Yeah.
Is this the same thing as saying that there's at least one node in C that's an ancestor of everything in C prime?
No, not quite. I'll show you. I think I can show you an example where that's not true. Because the depth first search has, you can order it so that you explore the sync component first. And in that case, the other ones won't be. There'll be cross edges. This edge could be. He's saying, does that mean this is an ancestor of this? Meaning this is an ancestor, a tree edge? No, and the answer is no, because this could be a cross edge. Okay. Okay, but you'll see this in the proof. Okay. Okay, so the highest post order number in C is bigger than any post order number in C prime. Okay, that's true. It's not true that every post order number in C is greater than every post order number in C prime. That's not true. Okay? Okay. So here's the proof. So we're just looking at C and C prime. Now we're just drawing the figure for two strongly connected components, C and C prime, right? And there's an edge between them. Okay? That's what we're going to prove it about. If a node V in C prime is explored first, what happens before it's returned? Does it explore, say in C prime, one of these nodes V, these are all labeled V, those are all labeled U. If one of these nodes V is explored first sometime in the depth first search algorithm, before any node in C, what happens? Do you explore all of C prime? And then you return. And then only later do you start exploring C, right? If a node V is explored first, Explorer V gets all of C prime, right? And then returns. And it doesn't go to C. It explores nothing in C, right? Okay. This is a cross edge, okay? So every node in C is explored after every node in C prime because we assume that a node in V is explored first, right? Okay. So that's, in that case, we're good. What's the other case? If a node V in C prime is explored first, then we're good. What's the other case? Yeah, there's a node in, this also is equivalent to saying every post-order number of C is larger than every post-order number in C prime. Right? It's just the post-order numbers are telling you when they're explored, or when they're popped off the stack. Okay. Now, if a node U and C is explored first, what happens? Here, all of C and C prime will be explored before returning. Right? Because this is strongly connected, so clearly the first node explored can see every other node, right? It can reach every other node, and it will explore all the nodes it can reach in C. It can also reach every node in C prime, because it can use this edge to go across. And now from any node in C prime, you can reach every other node in C prime. Okay? So all of C and C prime will be explored before it returns. Okay? From Explorer View. Okay? Explorer View happens. When Explorer View returns, everything in C and C prime will be explored. They would all have returned. Right? So all of their post-order numbers would be less than this guy's post-order number. And this guy's in C. So there exists a guy in C whose post-order number is higher than everybody else's. Okay? So U has a higher post-order number than any node in C. C prime. Okay? In fact, it has the highest post-order number of anybody in C and C prime. Okay? But yeah. And that's the proof. Okay? So it's a kind of slightly complicated statement, but that's it. Okay, so now, great. Okay, so now, this is great. Okay, well, almost great. If I could change the O-R, this thing to I-N-K, it would be great. It's like source. I wanted to find a node in the sink. Okay. So what should I do? Yeah. I don't know the SCCs. Yeah. Yeah. Yeah, did you see that? If I was like athletic, I would actually flip. But he said flip all the arrows, right? But if I did that, I would injure myself. The people would come and I would be carted away. Yeah, but he said flip the arrows. So what he said, we have this, the highest post-order number of this node. Does every node in C have a higher... Well, this is just test your understanding. I can't test your understanding, but I told you. Does every node in C have a higher post-order number than every node in C prime? Which one? B. Okay, that's not quite what we proved. Okay? Like, here's an example. I could explore A, explore B. We already saw an example, but let me just show you again. Explore A, we'll call explore B, we'll call explore C. Now, C's post-order number, and then you explore D. C's post-order number is less than D's. Right? So there exists somebody in here whose post-order number is less than the post-order number of the downstream component. Okay? Okay. So... But yes, this was the algorithm. That was the property we have. They don't match up because in the algorithm we need to sync a node in the sink, and this one says a node in the source. So this is a problem. Uh-oh. How should we fix this? You want to find a node in the sink component, right? You just reverse the edges. Right? If you reverse the edges, what used to be the source component... what used to be the sink component is now the source component, right? It doesn't change strong connectivity inside the components because all you've done for the cycles is reverse the edges, so you go the other way around the cycle. So the strong components will be the same, but the DAG will be oriented in the opposite direction, right? So now the source component in GR is a sink component in G. Okay? Okay, so here's the algorithm. You run DFS on G sub R to compute the post-order number. Okay, you take the graph, you reverse all the arcs, you write the adjacency list. It's a little puzzle that they sometimes give you on the coding interviews. How do you reverse the edges in a graph? You should look it up. Now, what the highest post-order number vertex V in GR is an async component of G, right? Of G itself, of the directed graph G. Now, you output the nodes visited in Explorer V, and that's going to give you all the nodes in the sync component, all the vertices in the sync component. Now we're still stuck. We still have a little bit of a problem. Now I want to repeat. Okay? So I did all this work to find one node in the sync component. Okay? And now I explored the sync component. What do I do now? Do I run DFS on the reversed graph again? That would take a long time because now I would look at that graph over and over again. Right? We want this to be fast, linear time. You can't look at it too many times, right? Okay. We could recompute this DFS in G sub R, or just use the same post-order number again. Okay? Because we have a very strong property. We don't just have this property, the highest post-order number is in a source component. We have this other, more complicated property. Well, let's just see. Okay? So if I take this out, now let's look at the highest post-order number and what remains. So first of all, what I did is I computed the reverse graph. Here's the reverse graph. And I wrote down the post-order number. So who has the highest post-order number? G. That's the guy in the sync component. Exactly like I promised. Right? So now we're going to explore from G, where will I reach? Now I'm exploring here in the regular graph, in G, not GR. I'm only going to see G. Now I'm going to remove it. Okay, so now what's left? Where's the highest post-order number? In this blue component. 12, right? That's the highest post-order number left from the reverse graph. So now if I explore that, can I reach any node in here? So I get only the nodes in only the vertices in that strongly connecting component. Okay? Okay, so and now what's the highest post-order number that's left? 6, right? Which means I do my DFS from A, which will get all of these 3 nodes. Okay. And I get those are my strongly connecting components. Okay, and what is the property? Why is this true? Well, how do I know it's going to be in the red component, the highest post-order number left? Okay? I know everybody in the red component, this property tells me that red component, because I did the DFS in the reverse graph, there exists a node in the red component, C, take that to be the red component. In the reverse graph, this edge goes the other way. So there's an edge from C to C prime in the reverse graph. So it tells me there exists a node in the red component, in C, whose post-order number is higher than everybody in the blue component. Right? Okay. So that's what it says. And so therefore I know that once I remove the green component, the next highest post-order number must be in a sync component. A source component in the reverse graph and a sync component in the forward graph. Okay? And then we get this thing. Okay, so first explorer of G, it removes a sync component, removes a source component of G sub R, right? The highest remaining post-order number in the remaining graph in G sub R is in a component with no in edges, okay? Is in a source component of G sub R. So V is in the sync component of G. So that's what we did first. Okay, and that's how it works. And then you sort of repeat, because now you have this property. You do this DFS of G sub R. You run the undirected components algorithm on G. That's all you're doing. Right? Remember in undirected connected components, you just explored the whole component and output it, and then went to another one. Okay? But you do it in reverse post-order number from step 1. Okay? And that's it. It's order V plus E time. Because this DFS, it takes V plus E time, and this undirected connected components algorithm took V plus E time, order V plus E time. Now, the question is, can you compute G sub R in linear time? you have to compute this reverse graph. Okay? That's an exercise left to the reader. Okay? So that's the algorithm. So here's the example again. I don't know, you probably saw it. First, what I did is I reversed the arcs here. Okay, once I reversed the arcs, I run DFS on this. G is going to have the highest post order number because G is in the source component for this graph. And then I remove C, and then this one and this one. And you can again think about runtime here. Like when I do the explore with the connecting component, first I did this first thing, which took order V plus E to reverse the graph, and then do DFS. And then this last component, this last thing, when I do the explore, I only touch the nodes in the green component. I only touch the nodes in the red component. I only touch the nodes in the blue component. And that tells you it's linear time. Okay, how I learned to love the stack. This is from last time. This is what we did today. Okay, and the observation is the highest post order number is in the source component. And then we can just reverse to find a vertex in the sink component. Okay? So from this outline, you should be able to reconstruct the algorithm.